Okay, we are here today to talk about IP subnetting. We'll cover IPv4 and IPv6, but we're going to start with the basics and kind of work our way up. So when we're talking about IP subnetting, what do we actually need to consider? What does it mean to be a subnet? Well, typically when we're talking IP addresses, we have a couple of things to worry about. We have the IP address itself, and then we have the subnet mask that goes with it. Now, when we're talking IP addresses and subnets, there's a few considerations, and I'm going to go ahead and write them down here. The considerations are: one, what is the subnet? What is that network? So we need to identify that network somehow. So the network ID. What is it? And that's usually given by a combination of the IP address and the subnet mask. Now with the subnet mask, we figure out how big the network is. So what's the size of that network? And we can also take the IP address plus the subnet mask to figure out exactly which group of addresses we're talking about. So what's the group? What's the subnet? Exactly what's my beginning and ending addresses? And what addresses can I talk to locally without routing? These are the main considerations that we're going to worry about. Now, one thing that a lot of people struggle with is how to actually figure out what your subnet is based on your subnet mask, how big it is. Well, when we're talking about IP, it's represented in a format that I'm sure we're all familiar with, but we have we'll use a very well-known example, 192.168.0.1, and this is usually accompanied by a subnet mask of 255.255.255.0. And for those of us out there that are a little more familiar with subnetting, we'll know that this is a /24 if we're using the CIDR annotation. Also, this is known as a class C. And we'll get into the CIDR a little bit more. So this is a CIDR notation. But let's take a look here at some of the IP addresses. So the first thing that we need to do is be able to convert these to binary, because that's how everything's handled on the back-end side of things. Everything is done in binary. This representation, the 192.168.0.1 for the IP and the 255.255.255.0 for the subnet mask, are just easier human readable annotations that represent the actual data in the background. So let's go ahead and look at the IP address, and let's actually convert that to binary. So those of you that might not be familiar, binary is base 2 numbering, right? So this is binary. And that's really simple because it's the way computers think. It's with ones and zeros, on or off, there's power or there's no power. This is how a machine thinks. So this is how we actually have to represent the IP addresses in order to understand the logic behind this. Now, in comparison, we typically use in our day-to-day, well, that is a horrible B. There we go. We use base 10 numbering. And this is called decimal. This is the numbering scheme that you're familiar with. 10, 100, 1,000. This is what we work with every day as people. Now base 2 is ones and zeros. So if you're seeing the pattern here, base 10 means that every value or every integer, every space can have up to a value of 10. So we have the values 0 through 9. That gives us 10 different combinations that we can use per space. Base 2 has two different combinations that we can use per space or per digit, and that is a 1 or a 0. So if we want to do more than a 1 or a 0 to a 1, I would say, we need to go to the next spot. So just like in the decimal system, when we hit 9 as a number and we want to represent 10, we now have, let's actually draw this out, but we have the 1 spot. So how many 1s? We have the 10 spots. How many 10s? Let's write this out, right? So we got 100, and it keeps going, right? So 1,000. So each digit represents one of these value schemes in base 10. So if we want to represent a number like, I'm just going to pick a random one, but 1,234. We have to look and say, out of these numbers, right? Let's think about that. Now this is really easy because we're doing literally a base 10 number to a base 10, but we know that there's 4 1s. We know that there's 3 10s, 2 100s, and 1 1000, and that makes up our base 10 number of 1,234. Now we're going to pick a smaller number and look at the base 2 or binary method. So with binary, remember, we only have 2 values, a 0 and a 1. So we have the 1's place, the 2's place. Let's do this to make it easy to tell it's a digit. The 4 place, the 8 place, and it keeps going in the same fashion. So if we wanted to represent a number, let's go ahead and say 12, okay? We know that 12, and it's easier to work from left to right. We know that 12 has 1 8 in it. So 12 minus 8 is 4. So we know now if we want to make 12, we can also do 1 4. So that would be a minus 4 here. And now we know that we can't fit any 2's and we can't fit any 1's. So 12 in binary equals 1100. So let's go ahead and actually convert this number here. So 192, now addresses are made by octets. So we have the first octet, the second octet, the third octet, and the fourth octet in IPv4. We will cover IPv6 later. Now each one of these octets is actually made up of 8 bits, and there's 4 octets. So if we actually convert this, and we'll start with 192. 192, so let's do 192 equals, let's go ahead and reference our decimal chart. We're gonna, or I'm sorry, not our decimal chart, our binary chart. We're gonna draw it out up here just for quick and easy reference. We have 1, the 2 spot, the 4 spot, 8, 16, 32, 64, and 128. Now you'll notice here that we can only go up to the 128th spot because we have 8 bits to represent, which means that we're going to have 8 values here that we have to populate. So since we can go up to the 128th spot, the next spot, which we can't use because we're only allowed to use 8 bits, would be 256. Because 128 times 2 is 256. Now, interestingly enough, we can use these 8 bits to represent 256 values because 0 is a value. That's very important to remember. All zeros is a value too. So even though we can only go up to 255 in our numbering scheme, we have 256 values available to us. So if we look at 192, we know that we can fit 128 in it. So let's go ahead and do 192 minus 128. And that would be 4, 6. So we have 64 left, right? So we're going to go ahead and put a 1 in this 128th spot. Or up here, we'll write it, right? Now, can we fit any 64s? Yes, we can, because that's all we have left. So 128 value and 164 value equals 192. However, we do have to fill in the trailing zeros. And so there's 192 represented with 8 binary bits. Now let's go ahead and do the same for 168. So 168 equals, let's do the same exact thing. Can we fit any in 128? Yes, we can. So if we were to do the math again, let's go ahead and say 168 minus 128 equals 40. So now can we fit any 64s in? No, we cannot. So that's a 0. So we still need to do 40 values here. But we can fit a 32. 32 is less than 40. So we can have a 32 value. And we'll subtract 32 from our 40, which leaves us with 8. So now we're in the 16th value here, the 16 column. We can't fit any 16s. However, we can fit an 8, as that's all that we have remaining. And we'll put in the trailing zeros. So that is 168 in binary. Oops. Now 0 is a really easy one, because as you can probably guess, 0 is all zeros. 8 zeros. And 1 is extremely easy, because we have 0, 0, 0, 0, 0, 0, 0, 1. Because the only value we can fit is this one spot up here. Now, we have to actually do the same thing for the subnet mask. And subnet mask is very easy because it's using the value 255, which, if you remember, our next spot after 128 is 256. So that means in order to represent 256, we need to have a 1 in the 256 spot, followed by all zeros. But we're not allowed to use the 256 spot, and regardless, we're only trying to make the number 255. So that's really easy, because 255 is all ones. So 8 ones is 255. Now, what I'd like to do here is we're going to go ahead and erase this. And I'm going to go ahead and write out the full IP address and the full subnet mask, as tedious as that's going to be. So that way we can kind of reference them. So we'll start with the IP. So 192.16.0.1 equals 1100.0000, and the dot, which denotes that we are crossing an octet. So this is 1 octet here. Now we'll go down to 168, which is 10101000, and then 0 is super easy. We have 00000000, and then 1, the last octet, is also very easy. 00000001. That's 192.168, which I messed up writing. .0.1. Let me rewrite that. 168.0.1. Now, down here a little more, we're going to go ahead and write out the subnet mask. So 255.255.255.0 equals 1111. So this is going to be 3 octets of all ones. So an octet is 8 bits. Followed by an octet of all zeros. And this is one of the most common subnets that you're going to see out there. So typically, your home routers, a lot of things like that are going to use these class Cs, these /24s, or this subnet here as their network. So you're going to see this a lot. And this is also very easy to demonstrate and figure out. And we'll see why in a minute. So let's go ahead and take a look deeper into that. So we're actually going to start on the subnet mask, because what we're trying to do is identify, one, what is this subnet? What's its range? How big is it? And what does it include? So when we look at the subnet, we can see, especially in binary, that it's all ones on the left and all zeros on the right. And this is going to be true for any subnet mask. The amount of ones and the amount of zeros can vary, and that's what adjusts the size of the subnet. But they do have a very specific meaning. A 1 in the subnet mask indicates that that bit is representing the network ID. A 0 indicates that it is representing a host address. So let's go ahead and we'll mark this. So in this case, it's easy because the first 3 octets are representing the network ID. And the last octet is representing the hosts. This is why this particular subnet is easy, because it's easy for the human mind to follow it. And we'll do a little bit more of a harder to follow one after this as an example. But the network ID says all of these bits are going to represent my network. Meaning if these bits in an address are different, in this case, the first 24 bits here, this is why it's a /24 in the CIDR notation, the classless interdomain routing. So this says /24. That means that the first 24 bits represent our network ID. So if these bits are different, then it's a different network. It's a different subnet. So if we look up here at our address and we actually convert this to the address, we know that these bits now are network ID. And these last bits are the host ID, or the host addresses. So these ones here, the host addresses, are allowed to change. And they're all part of the same subnet. They're all part of the same network. They can talk freely to each other without using routing. If the net ID is different, then it's a different network. We're going to need to implement routing or be on the same local device in order to hit those addresses. They're a different subnet. They're a different network. So we talked about what CIDR is and how it's determined. In this case, this is /24 because the first 24 bits indicate what the network ID is. And the last 8 bits indicate the hosts. The host identifiers can change. You can have, in this case, 256 addresses in this subnet. But the network ID cannot change, otherwise it is a different subnet. And we garnered all of that just from looking at the subnet mask, and then we use that to apply it to the IP address. So let's go ahead and actually look at, we'll grab a different color here. Let's go ahead and look at a different subnet mask. So let's say instead of /24, let's say we're talking about a /25. So let's go ahead and change this to a /25. Now we know that the first 25 bits are going to be our network identifier.
So let's go ahead and convert our subnet mask. So our subnet mask would be 255.255.255, and now this is the weird one, .128. And that's going to equal, and you would actually do this backwards, right? You would do the binary version first before you did the this base 10 version, because you would figure out the base 10 version based off of the binary version. Okay, so here is our /25, and we can go ahead and confirm that this is in fact a 25 because we have 25 ones starting from left to right. And this is once again our network ID. And then we are only left with 7 bits of zeros here for our hosts. Now, what does this mean exactly? This one's a little harder to follow. But what it means is when we break the IP address down into binary, keep in mind, this is all done at the binary level. So the class C, the /24, was very easy for us to follow because the host bits actually followed one of the octets. So it left an entire octet. So we knew in a class C scenario or the /24, if we saw anything that started with 192.168.0, no matter what came after that, as long as these first 3 octets matched, it was part of our network. Well, with this one, it's not following the octet. The first bit in our last octet is used in the network ID. So this means that, it's a little harder for us to follow. But if we think about it from this perspective, it's a /25. The first 25 bits identify the network. And, you convert this out. So the 128 here that we got here, the .128, that's just converting this last octet into binary. So 10000000, which is the same that we have over here as our last octet, equals 128. That's where that 128 came from. So this number is very useful for us because we can use that to determine how many hosts are in this subnet or how many IP addresses. So in this case, it's 128. Very, very easy, right? It's great because now we know that if we look at the original Class C breakout where we're following the subnet, where we're looking at the subnet, we can know that anything following, so if we have .1, so 192.168.0.1. Well, we know that anything in this last subnet, right, 128, there can only be 2 groups of 128. So we know that the address is 0 through 127 because remember, 0 is a value. That's going to be a subnet. And then the numbers 128 through 255, because remember, the highest we can represent in binary and 8 bits is 255, the number. But we have 256 values because 0 is a value. So we know, in this case, that these are 2 possible subnets because that's all that's going to fit. And if we have .1, we know that we have to fall into this first subnet. So we automatically now know the size of our subnet is 128 addresses. And we automatically know that our range is 0 through 127. So what that means is any address that's outside of that range, So not only do the first 3 subnets have to match this 192.168.0, but it also has to be within the 0 through 127 range. If it falls into the 128 to 255, it is a different network. It is outside of our subnet. So not quite as easy to follow. And this, of course, we can keep going. We can go all the way up to 32 because there's 32 bits in an address. So the more we go, the little bit harder it gets to actually figure these out. But it's the same exact concept. And once you convert it into binary, it's very easy to see. Now with IPv4, IPv4 addresses are 32 bits long. That gives us about 4.2 billion address combinations that we can use. Now, IPv4 has been around, for a very long time. And as you probably know, there's a global shortage on this. So one of the, there's actually been a couple different solutions to help with this global shortage. One of them is NAT, Network Address Translation, which allows you to basically have public addresses that are available and visible on the public internet. And you can have private addresses which are local only to your local network. So they're not routable on the public internet, and you can translate between them. So you can have many private addresses translated to a single public address to kind of hide behind that and use it. That's a whole nother topic that we won't get into. But one of the other things that's more relevant is the release of IP version 6. Now, IP version 6 or IPv6 has a lot more address space. So IPv6 actually has 16 bits per octet, if you will, although it's technically not called an octet, I guess. But it has 16 bits per octet instead of 8. Remember, we have 8 because we have, let me grab another pen color here, we have 8 digits or 8 bits per octet, right? So in IPv6, there's actually 16 bits per octet, and there's 8 octets instead of 4. So that makes the address 128 bits long for IPv6 compared to the 32 bits that is present in IPv4. Now, in contrast, I'm going to write the numbers out here actually. So IPv4, we can kind of get rid of some of this. IPv4 gives us 4,294,967,296 addresses. Now IPv6, as we kind of talked about, and we'll get into a little bit more here. Now, this number is a little bit bigger, but I'm going to go through it just for the fun of it. IPv6 gives us a total combination of addresses: 340 undecillion, 282 decillion, 366 nonillion, 920 octillion, 938 septillion, 463 sextillion, 463 quintillion, 374 quadrillion, 607 trillion, 431 billion, 768,211,456 addresses. Yeah, that's enough addresses that if we were to give every atom on the surface of the Earth an IP address, it would only use a fraction of the available space. We would still have enough addresses left over to IP address the atoms on the surface of over 100 more Earths. So we would use less than 1% of the available IPv6 space if we gave every single atom on the surface of the entire Earth an IPv6 address. I think it's safe to say we're not going to run out of these. But anyway, that's more for dramatic effect than anything. But back to the business, when we're talking about IPv6, it's the same exact concept, just on a bigger scale. So we still have subnet masks, we still have IP addresses. We have to figure out how big our subnets are, and we have to figure out, well, a lot of things. But with IPv6, it's done in hexadecimal. So whereas IP addresses are done in binary, at the back end everything's binary. We represent it in base 10, right? 192 means 192, whereas IPv6 actually uses hexadecimal, which is the numbers 0 through F. It's actually base 16. So base 16 equals hex. Now what does this mean? This is the same exact concept we talked about before, the difference between base 2 and the difference between base 10. The biggest difference is now each value spot is representative of 16 values. So how do we do that? Our numbering only goes up to 9, right? We have 0 through 9 that we can utilize in base 10. Well, the answer to that is we need more values that we can utilize. So hexadecimal actually borrows from the alphabet. So we have the same values 0 through 9 that we can utilize. But when we get to 10, instead of going up another space and using a 1 in the tens value, we're actually going to use the letter A. So A equals 10. B equals 11. C equals 12. D is 13. E is 14. And F is 15. Now the same thing with base 16. That means that we have 16 values. So base 16 equals 0 through F. And you're probably thinking F, you only said F goes up to, is equal to 15. Well, that's true because once again, 0 is a proper value. So we actually have 16 different values because it's 0 through F. And it's kind of the same thing, right? So we have, if we look at our same spots, so we did the binary conversion up here. Now if we look at these same spots, we have a 16 spot and we have a 32 spot. And that's pretty cool. So anyway, we can represent this with 16 bits. And the way that we do this is hexadecimal is usually done in pairs. So if I want to represent the number, let's say 16, for instance, 16 would actually be 10. So, this is our normal numbering system on the right, base 10, and on the left is hex. So 10 equals 16. Now that's, I'm sorry, I messed this up. I drew that wrong. This is actually the 1 spot, and then we have the 16th spot for our hexadecimal notations. Sorry about that. So hex is 10 in base 10, that equals 16. So it's the same, the same exact concept here. The only difference is the numbers we're working with now are hex instead of base 10. So when we want to do the actual conversions, it's easier for us to convert from hex to base 10 and then base 10 into binary. Now we're not going to do that because it's the same exact thing that we just went through. only bigger, bigger numbers we're talking about, and more octets, and more bits per octet. Remember, there's 16 per octet now instead of 8. But it's the same thing. Now, we talked a little bit about CIDR notation up here before. Now, in IPv4, this is just an optional way to refer to a subnet that makes it easy to determine the size, right? The Subnet Mask also tells us that, but it's just another way to represent that same data, right? 255.255.255.0 is a subnet mask, is the same exact thing as a /24. A network engineer can look at that and know that that's the fact. Now, when we start talking about weird size subnets, oftentimes we might have to do the conversions or look it up. But you can sit and figure it out, and you're going to find that those two are completely equivocal, right? They're representing the same thing in a different way. With IPv6, we only use CIDR notations because of the size that we're talking about, because of the 16 bits per octet, and because of the 8 octets. And I keep calling them octets. They're not technically octets because they have 16 bits, but that's what we're going to call them. Because of the size of that, it just doesn't make sense to do the kind of long written out version of the subnet mask that we oftentimes do with IPv4. It just doesn't make sense, so we're not going to do that. We're only going to use the CIDR notation. CIDR. Now, when we're doing the CIDR notation, an IPv6 address is 128 bits. So that means we can go all the way from a /0, which just like in IPv4 represents everything, all. And we can go all the way down to a /128, which is a single address. Just like in IPv4, so this is IPv6, in IPv4, a /32 equals a single address. That means that its subnet is literally just that one address, just itself. It has to be routed in order to hit other subnets or other addresses or on the same local device. Now, on IPv6, we're going to cover just one more topic, and that's going to be the actual, what does an IPv6 address look like? So an IPv6 address, like I said, is represented in hexadecimal. So a good example of one, and I'm just going to make one up off the top of my head, but a good example of one would be like, say, 2001 and colon is how we separate the octets now. You don't use a dot, you use a colon. This is hexadecimal, after all. And then 2702 colon, and we'll come back to what that means here in a second. And then we'll say 1 / and we'll do a 64. So what does this exactly tell us? The double colons, one cool feature about IPv6 is they're very long addresses, right? But if you have octets that are all zeros next to each other, you can once per address, you can remove all those zeros by placing a double colon. So if we were to actually write this full address out, it's going to be a bit longer because the eight octets. But the first octet 2001 colon, the second octet 2702, the third octet 0000, the fourth octet 0000, fifth octet all zeros, sixth octet all zeros, seventh octet all zeros, and then the eighth and final octet would be 0001. And then this would be /64. So it was built into the protocol to be able to shorten your addresses by removing big strings of zeros. Now, this can only be done once, though. So another thing is you can remove leading zeros within the octet. So you'll notice when we wrote 1 here, we removed the 0001 It's just 1. That's fine. Leading zeros can be removed the same that they can in an IPv4 address. However, octets of all zeros can only be truncated or shortened, removed once. So if we have an IP address like, let's do the same, 2010:0:2702:1, right? So there's an octet of zeros here. We have to keep it in because we can only get rid of one group. And in this sense, it makes more sense to get rid of these 4 octets that would be in this spot than it would be get rid of this single octet of zeros. So we can use that once per address. You can't use it more than once. Now the 64 over here, the /64 that we talked about, that's the same exact thing. That means that the first 64 bits of the address, when we convert it to binary, are ones. And that's what the network ID is. So 64 bits out of 128 means that the remainder 64 bits are going to be our host addresses. That can change as so long as the network ID doesn't change. And they'll be within the same subnet. So the same exact concepts we talked about before, just on a much, much, much larger scale. Okay, so let's go ahead and actually convert the first octet of this IPv6 address, 2001, right here. Let's actually go ahead and convert that into binary. Now, for us as humans, it's going to be easier to convert into base 10 or decimal before we actually make the conversion to base 2 or binary. Now there's calculators online that will do this for you automatically. So you go straight from hexadecimal to binary. However, for illustration purposes, we're actually going to do it out here. So in hexadecimal, it's not 2001, it's 20 and 01. We go in pairs in hexadecimal. So we have 20 and we have 01. Now we have to convert each of these separately into base 10. So if we look at this, so 1, we have a 1 in the 1 spot and a 0 in the 16th spot. So that is, this is hex, so that equals 1 in not binary. That equals 1 in decimal. Well, I suppose it does equal 1 in binary too. But anyway, now 20, we have a 2 in the 16th spot, which is 32, and a 0 in the 1 spot. So 2 times 16 is 32, so we have 32. Now we have to convert each of these into our binary. And if you remember, in IPv6, each octet is 16 bits instead of the 8 that we have in IPv4. So we have to make sure to take that into account. But first, let's do 13. If we kind of look up here into our key that we made before, let's go ahead and erase some of this. But if we look up here, we can see 32, very easy. We have a 32 spot. So 0 128s, 0 64s, 132 value, 0 16s, 0 8s, 0 4s, 0 2s, and 0 1s. And so that gives us our 32 value. Now, once again, this is 16 bits, but this is the first 8 is 32. So this is going to be 0 0 1, 0 0 0 0 0. And now 1 is going to be the leading 7 zeros and a 1. And this is our octet in binary. That is 2001 in hex. Well, thank you for watching. I hope that you took something away from this video, and hope you also have a wonderful day. Thanks again.